Welcome back. In this video, we're going to begin Chapter 7 on thermodynamics. And the goal of this chapter is to give you a review of the fundamental concepts of thermodynamics. It's not intended to be a comprehensive treatment, which would take a whole semester to do. Here, we're just interested in going over the fundamentals and also to establish the language, as I say, the vocabulary, and the notation that's used throughout thermodynamics. Mastering the material in this chapter is a necessary step in our goal of learning how the microscopic behavior of atoms and molecules leads to the emergent macroscopic properties of matter. So specifically, this chapter is going to prepare us for the next chapter on statistical thermodynamics, where we derive expressions relating the microscopic equations and motions of atoms and molecules to the macroscopic properties of matter. Now, anytime you're working with thermodynamics, it's important that you understand what you mean by the system. How do you define the system? How do you define the surroundings? And how do you define the boundary? How do you specify the boundary that separates the system from the surroundings? And the boundary is what regulates the flow of energy and matter between the two. Now, how you define the system really depends on the problem you're working on. In one particular problem, you may define the system one way with the surroundings and boundary, but in another problem, you might define the system and the boundaries and the surroundings differently. Even though it might physically be the same thing that you're looking at, the way you specify what's the system and the boundaries and the surroundings could vary from how you want to treat the problem. So you want to be clear on how you're treating the problem and what you're defining as the system, what's the surroundings, and what are the boundaries. But it's very important that we be clear about what we mean by these definitions, of course. So here's our definition of system and surroundings. And by boundaries, which could be real or they could be hypothetical boundaries between the system and surroundings, these will regulate the flow of energy and matter. So two adjectives, a pair that we often use, are permeable and impermeable. When a boundary is specified as permeable, it means that matter can flow between the system and the surroundings. And conversely, if the boundary is specified as impermeable, then no matter can flow between the system and the surroundings. Now, sometimes we can have what's called a semi-permeable boundary, where certain chemical species or species can flow between the system and the surroundings, but others are prevented from flowing. So, for example, if you have like a battery where you have a separator and you want the electrolyte to flow back and forth between the cathode or anode side so that you have charge balance, but you don't allow the redox species to go, then that would be an example of a semi-permeable boundary. Another pair of adjectives we use are diathermal and adiabatic, and these should be familiar to you if you have your coffee cup, which has some kind of Dewar coffee cup so that it stays warm longer. That's an example of an adiabatic boundary. An adiabatic boundary prevents heat flowing from the system to the surroundings. A diathermal boundary, on the other hand, like if you had a good frying pan and you have heat underneath the frying pan, you want the heat from underneath the frying pan to transmit through that boundary to whatever it is that you're cooking in the fire pan. So that would be an example of a diathermal boundary. So a diathermal boundary allows heat to flow, and an adiabatic boundary prevents heat flow. All right. Another pair of adjectives that we'll use is non-rigid or rigid. And this is defined particularly with regard to the possibility of mechanical work being done on the system or by the system. So when we have a rigid boundary, that means that the system is not able to expand. The volume can't increase, the surface area can't change, it can't change its length. That means that when we have that situation, we call that a rigid boundary, and there's no ability to do mechanical work, which we'll come back to in later slides here. So a non-rigid boundary would then allow those possibilities, would allow the system volume to expand or the expansion of the length or surface area to change and things like that. And also it's important in thermodynamics, when we talk about an isolated system, we mean very specifically that no energy or matter can flow between the systems and the surroundings. So this is the strictest of all possible boundaries. An isolated system has a boundary that prevents all energy and matter flow between the system and the surroundings. Okay, so it's in sort of common usage, you might say, oh, I'm feeling isolated today, but in a thermodynamic sense, you don't want to feel isolated because that means that you would die soon because there's no energy or matter, particularly matter, no food or air is going to be flowing into to your environment if you were actually thermodynamically isolated. Okay, so isolated has a very specific meaning in thermodynamics, and it's regard to the boundaries allowing no energy flow or no matter flow between systems and surroundings. Now, in thermodynamics, we're going to be interested in equilibrium states. What are the macroscopic properties that the system has once it comes to equilibrium? And it can be in various types of equilibrium states, and we're going to see how we can connect those equilibrium states. But once it's in that state, then it's going to have certain properties that we're interested in how to predict them. And when we're dealing with our thermodynamic system, when we want to know, is the system in equilibrium? Has it reached equilibrium? Well, it depends on how long you wait. So in a sense, thermodynamics doesn't have time involved into it, but time is actually sort of assumed that you've waited long enough that all of the properties of the system are not changing. So when we have an isolated system, we'll say that the system, isolated system, is in equilibrium when we see that all of its macroscopic properties have become time independent. They're not changing anymore. So that definition is pretty simple. Whenever the isolated system's properties stop changing in time and they're constant, then we know that system has reached equilibrium. But more interesting problems are going to be non-isolated systems. In that case, we can have the energy and matter flowing between the system and the surroundings. And in that case, we have two conditions for determining whether that system is at equilibrium. First, we have the condition that the macroscopic properties need to be time independent, so they stop changing. But the next condition we require is that if you take that non-isolated system and you make it an isolated system, the properties should continue to remain time independent. If you take an isolated system that appears, a non-isolated system that appears to have all its properties time independent, and you isolate it, and then the properties start changing, then you did not have a system at equilibrium. In fact, what you had was a system that was in some form of steady state. So you can imagine if you had like a piece of metal that has one end on a hot plate and another end on a piece of ice, then there'd be a temperature gradient, and over time, that might be come a constant temperature gradient, and its properties would look like they'd be time independent. But if you separated it from the hot plate and the ice, big piece of ice, then you would find that the temperature gradient would start to go away and it would become a uniform temperature. So that was an example of a system that was at steady state and not at equilibrium, even though it appeared that its properties were time independent. So again, a non-isolated system, properties are time independent, and isolating the non-isolated system leads to no further changes in its properties, and they stay time independent. So again, if one is true but two is not, then you are probably likely in a steady state situation. Now, in thermodynamics, we're going to be interested in equilibrium states and the properties of the system in those equilibrium states. And when we describe those properties, we're going to describe them with what we call state functions. So these are properties that depend only on the system's equilibrium state. They're not dependent upon the history of how you reach that equilibrium state. So you might use one process to take you to an equilibrium state, or a completely different process to take that system to the same equilibrium state. The state functions are those properties of the system that are independent of how you got there. They only depend upon its current state, current equilibrium state. All right? And among those properties, we're going to classify them as extensive or intensive. So you can have an extensive property is a property that depends linearly on the amount of substance that you have. So you imagine if you take, if you had a perfect cube of a substance and you made, and it was at equilibrium, and you made a clone of it, and you took that clone and you pieced them together to make a rectangular cuboid, then you would have like the temperature of that object. If it was identical and you bring it together with another object with identical temperature, then the temperature stayed the same. So that's actually an example of an intensive property, which is independent of the amount of substance, whereas the mass of the two cuboids, when they were put together, doubles. That's an example of an extensive property. So extensive properties will depend linearly. So if you double the material, then you have double the property. whereas intensive properties are independent. So as an example, temperature or the density is going to stay the same when you double the amount of material if they're two identical systems that you bring together. There are properties that are neither intensive nor extensive. So for example, if I had two cubes, and I brought them together and I made a rectangular cuboid, the surface area is going to increase, but it's not going to double. So surface area is actually a property that's neither intensive nor extensive. You can always create an intensive property from an extensive property by just dividing it by the amount, scaling it by the amount, so the number of moles, or the mass. So you can create what's called the molar quantity. So if I took the volume and I divided by the number of moles, I'd create the molar volume. If I took the volume and I divided by the mass, I would create the specific mass. So the molar volume and the specific volume. The molar volume and the specific volume are examples of intensive properties, whereas the volume is an example of an extensive property. It's also important when we're doing thermodynamics to understand what we mean by the different types of phases that are present. And when we think about thermodynamic phases, then we start thinking about how the system sort of exists in regions of space. So if the system throughout a region of space has all of its intensive properties identical in any point in space. So if I was in some solution and I looked at this point in the solution and this point in the solution and this point in the solution, and the temperature was exactly the same at all points in the solution, and the density was all the same at every point in the solution, these are all the intensive properties. If they're constant throughout that region, we would say that that system was in a uniform phase. All right. Now, we can also have a system that we call homogeneous, and a homogeneous is one where the intensity properties can vary. So maybe you have a solution and the temperature here is 89.8 degrees, and slightly over here is 89.87 degrees. Then what's happening is that there might be a continuous variation in the intensive property, but it's continuous throughout space. That's what we call a homogeneous phase. In some textbooks, sometimes we'll use these two interchangeably, and it can get confusing, but we're going to be very specific here. Uniform means that it's constant throughout space. The intensive properties are constant. And homogeneous means that they can vary continuously throughout space. Whereas heterogeneous means you have discontinuous change in the properties. So the density may be one value here, and then it discontinuously changes to another density here. So an example would be if I had a glass of ice water with ice cubes floating in the water. If you were in the liquid part of the water, you'd have one density, and then if you moved into the region where you were into the solid water, the ice, the density would change discontinuously. That would be an example of a heterogeneous system. And so when we talk about the regions of space, whether they're uniform, homogeneous, or heterogeneous, this is what we mean. And then also when we're talking about the phases of a material, then we're talking about the region of the space where the system's physical properties are all homogeneous. So when we use this term homogeneous, when we say that we have a region of space where all the intensive properties are homogeneous, then that's a phase. That part of the system is a particular phase of the system. So the phase could be a gas phase or a liquid phase or a solid phase. Or you can have two liquid phases. For example, you might have an oil and water mixture where you have one region where you have a homogeneous region where it's all water, and it's liquid, another homogeneous region where it's all oil and it's liquid. That would be an example of a heterogeneous system, but inside that heterogeneous system you have two different phases, the liquid water phase and the liquid oil phase. Okay? So when you have several systems, then again, systems with several phases, then that's an example of what we call a heterogeneous phase. Now, when we're talking about matter, we know that there are electrostatic forces we learned in the previous chapter that will cause the atoms and molecules of matter to become attractive, and then they will come together and aggregate into from the gas phase into a liquid phase, and then it can aggregate even further into a solid phase. And in thermodynamics, we make the distinction between solid phases and fluid phases just by the fact that when you're in a solid phase, the phase will resist deformation. So if you apply some kind of shear stress to it, so if you took an object and you kind of applied a shear, we go back to chapter 1 and look at the section on applying shear shears to an object, then you can see that when you apply a shear stress to an object, and with a solid, it will sustain that shear and stay sheared. Whereas a liquid or a fluid phase, if you apply a shear to it, then the molecules will move in response to that, and the shear stress will go away. So you can't support a shear stress in a fluid phase, whereas in a solid phase you can. Now, within the context of a fluid phase, we could further distinguish between liquids and gases, which is sort of the definitions that you probably learned in your high school chemistry. And generally speaking, all of these are a little bit slightly subjective, because even solids, if you apply shear force stress to them, over time they will start to deform and they will not support the shear stress fully. So it's somewhat relative here, but it depends on sort of the time scale in which you're looking at these things. But liquids and gases are fluids that won't support a shear stress. And what distinguishes liquids from gases generally is that a liquid has a density that's relatively insensitive to changes in temperature and pressure, whereas a gas, if you change the pressure, it will change its volume dramatically. So a gas density will approach zero as the pressure is reduced at a constant temperature. And I just mentioned here plasmas is another possible phase, but we won't really be discussing that in this class. So finally then, when we get to what we call equations of state, we've talked about these equilibrium states and how they have all their macroscopic properties at equilibrium. And there should be relationships between the equilibrium properties in one state and another state, and within those properties within a particular state. So in the equation of state function, we learn that some equilibrium state is going to be uniquely defined by a small set of state functions, of equilibrium properties. So we're going to say that there are n independent state functions, and I'm going to just generically leave them as just x1 through xn. And these are what we call the independent functions. And then from these, you can derive all the other state functions, which are the dependent ones. So this relationship between the dependent state functions and the independent state functions is what's called an equation of state function. And you may be familiar with the equation of state function. So for example, if you were working with a gas and it was you had it with diathermal and rigid boundaries, so that you had a constant volume and a constant temperature, then you might use a equation of state where your independent variables were temperature, volume, and the amount, say number of moles, and the state function would tell you how to predict the pressure given these three independent state functions. So an example of that would be the ideal gas law, where here the pressure is equal to nRT over V, R is a constant, NT and V are your independent parameters, and P is your dependent state function. Other types of state functions for gases might be, for example, the van der Waals equation, where you predict it. But that's just one example where we say it was convenient where we had diathermal and rigid boundaries so that we had a constant volume and temperature. But maybe you're working under conditions where you had non-rigid boundaries, so you might have a constant pressure and temperature. You might rearrange and make your independent variables temperature, pressure, and number of moles, and then volume would become your dependent state variable. So how you propose to write your state function and what you choose for independent variables and what you choose for the dependent variables really depends upon the problem that you're working on. But the bottom line is that for a system, there's going to be a set of n independent variables from which you can predict all of the dependent macroscopic equilibrium properties. All right. For example, also here when you have a mixture of S substances, then you might require an equation of state which is going to have a 2 plus S independent macroscopic variables. So if I had S substances in it, then my pressure equation of state might depend on temperature, volume, and then the number of moles of substance 1, substance 2, substance 3, and so on. Or if I did it in volumetric, it would take this form here. Now, a thermodynamic process is when we're going from one equilibrium state to another equilibrium state. And when we describe these processes, we're going to have a number of adjectives for that transformation. And let's go through a few of these adjectives here and see specifically, exactly what they mean. So when we talk about the expansion or compression of a system, then we're talking about the case where we're obviously just increasing the volume of the system or decreasing it, whether it's expansion or compression. That one's pretty obvious. So any process where the system goes from a state of low volume to a state of high volume, then that's an expansion process. And conversely, if it goes from high volume to smaller volume, then it's a compression process. That one's straightforward. An isothermal process is a process where we transform from state A to state B, and throughout the process, the temperature remains constant and uniform. So this is really specific, okay? So let's be clear about this. Isothermal does not mean that state A and state B have the same temperature. It's much stronger than that. It's saying that in the transformation of A to B, that the temperature remained the same all throughout that process. It remained constant and uniform throughout the process. That is what isothermal means. When we come to isobaric, isobaric tells us that the pressure remains constant and uniform throughout the system. So if we have a process where we transform to A to B and the pressure of A and the pressure of B is the same, it's isobaric if it stayed constant and the same pressure as it transformed from A into B. That makes it an isobaric process. Likewise, an isochoric process is a process where the volume of the system remained constant as it transformed between the two states from A to B. In an adiabatic process, which is again related to the name for the boundary, means that an adiabatic process means that no heat was allowed to flow in and out of the system as it transformed from A to B. No heat went in or out of the system. So that made that process adiabatic. We'll also talk about cyclic processes where you start at, say, some state A and you move to other equilibrium states, but in the process you come right back to A, then that's what's called a cyclic process. And that'll be important when we talk about thermodynamic engines later in this chapter. And then the last one here, which is a little bit probably conceptually the hardest one to follow, which we'll go to in some later slides here, is when we have a reversible process. And this is when the system remains infinitesimally close to equilibrium as it transforms from state A to state B. So you're transforming through these two, from A to B, and in that process, every point along the way, the system remains at equilibrium. Okay? So this is actually is just a hypothetical type of process. No process is truly reversible. No process is at equilibrium along the way, but it's an approximation that we can make in thermodynamics that can be a good one and will actually really help us as we work out the changes in the system properties through processes that are even irreversible. So when we talk about reversible processes, we say that we're infinitesimally close to equilibrium all throughout the process. So let's look at an example of what I mean in distinguishing between a reversible and an irreversible process. Say you have a system that is at equilibrium and in a bath that's at 350 Kelvin. So everything's at equilibrium. The system's in this bath. It's reached 350 Kelvin and it's now at equilibrium, and we pull it out and we plunge it into a bath at 273 Kelvin, where now it will start to re-equilibrate to this lower temperature in this bath. What does it look like in terms of the distribution of temperature as it transforms from the initial state, 350, to the new equilibrium state where it's going to be at 273? Well, if you might think about this, it probably doesn't take much to sort of imagine what's going on here. If we start out with our system at 350, and you imagine that since it's in contact with this cold bath here at 273, that it's the surface where it starts to cool first, and it cools from the surface inward. So we imagine that there's a layer where it drops from 350, say maybe down to 340 on the outside layer, and as it cools over time, then the outside layer cools first, and in the deepest center of it is where it remains the hottest, and we have this gradient of temperature throughout the cooling process where it's coolest on the outside as it's cooling and stays hottest on the inside until eventually all of that gradient disappears and we reach an equilibrium state where it's 273 throughout the system. This is an example of irreversible cooling. Now remember, reversibility is when you're at equilibrium at every point along the process. And clearly, when you have a gradient, temperature gradient like that, that's not an equilibrium state. So a reversible cooling situation would look like this. Let's say I took the bath here, and maybe I had a control over the thermostat on the bath, and I took it from 350 down to 349.99 Kelvin, and then I let it sit for a while, and then I took it from 349.9 to 9.98. So 349.98 to 349.97 to 349.96 and so on, and slowly lowered the temperature so that if you looked at the temperature gradients inside, there would be none, and the system would always be at equilibrium at all these temperatures until I eventually got it to 273 Kelvin at equilibrium. So that would be an example of a reversible cooling of the system. All right. The same is true for expansion and compression. So you imagine if I had a gas in a piston cylinder apparatus like this. Here's my gas that's at equilibrium, and then if I start compressing the gas, so I start pushing the piston in, well, if I do it irreversibly, as soon as I push the piston in, there'll be a region here where all the molecules are bunched up. So you can imagine that as I push the piston in, there'll be a higher density here just behind the piston face, and as I close it in, there'll be higher density here, but lower density over here, which is furthest from the piston. And this will eventually equilibrate, but in the instant that I push it in, there'll be a high density here and a low density here, and this will equilibrate on a time scale that's, say, on the order of speed of sound in there. So eventually there'll be a wave that kind of moves back and forth, and eventually this will equilibrate to the same pressure. But as soon as I push this in, there'll be some deviation in the uniformity here, and there'll be a higher density here and a lower density there. So this process, this irreversible compression, will not be at equilibrium during these intermediate steps because the pressure won't be uniform throughout. Now you can imagine the whole process, if we did an irreversible expansion, what that would look like. That would also, when you pull it out, you would have a lower pressure right behind the piston, and there'll be a gradient of pressure in there. You can imagine doing that drawing yourself, and you can see that in both cases, irreversible or expansion or compression, we will have a non-uniform density inside the cylinder as we do the expansion or compression. Whereas if we did this reversibly, then we would press our piston in ever so slowly in this reversible fashion so that we didn't allow there to become any kind of density fluctuations, any kind of gradients in the pressure inside this, so that it stays always at a uniform pressure inside throughout. All right? This is an example of reversible compression and expansion. Right? And you can always tell when you look at a process like here that whether it's reversible or irreversible, because if you had a movie of the irreversible process and you played the movie backwards, you could see that just didn't make any sense. So if you know when you see a movie played backwards, you can see right away that there's something physically wrong there. And when you play the movie of an irreversible process backwards in time, you can see that there's something physically wrong there. But if you played the movie of the reversible process, you can see that it would look perfectly fine whether it's going forward or backwards. Okay, so that's it for this. In the next video, we'll look at what we mean by heat in work and thermodynamics.